Okay, so we have a lot of useless information here. What we really need to know is that this part right here is our problem statement. So what I'm going to do is I'm just going to start from there, and then I can go back up to the top part and pull any information I need from there. So we want to find the required wall thickness of a shaft to the nearest 16th inch if its outer diameter is 4 inches. So we're finding the wall thickness, so it's hollow. So we want to find that T. Or we could also solve for the inner radius and then back solve for that T. Then we also want to find the diameter of the solid axles to the nearest 10th inch. The drive shaft and axles are both made of steel. We want to ensure the drive shaft and axles don't fail and to use an allowable stress of 1/2 the yield. So for steel, shear yield is 21 KSI. So that means our allowable shear will be 10.5 KSI. Okay, so for the tubular drive shaft, we are given the drive shaft is spinning at 3,225 RPM, and the system also has 840 horsepower. So to find out ideally we're going to end up using this equation, shear equals T rho over J, because we're in torsion. That's where we're developing that shear stress, is because of torsion. So first we need to solve for that T, that torque. We know power equals torque times angular velocity. We're given the power. We have 840 horsepower. But really we can't use horsepower. We need to convert that. So we're given the conversion of times 550 pound-feet per second. And we get 462,000 pound-feet per second. And that's really pound-feet per second per horsepower. So we get our power, 462,000 equals torque, we're trying to find that, times angular velocity. So we're given an angular velocity of 3,225 revolutions per minute. So on the left side here, we're in seconds, and we want to be in minutes. Or we can be in minutes, convert seconds, either way. I'm going to go ahead and cancel out the minutes. So in 1 minute, there's 60 seconds. And we also can't be in revolutions, we need to be in radians. So in 1 revolution, there's 2 pi radians. Revolutions cancel out, radians just automatically goes away. So we end up getting, so really we would get an answer in pound-feet, but we want to convert that to kip-inch. So that will be 16.4 kip-inch. Now we're doing that because our shear is given in KSI, kips per square inch. So ideally we want everything to be in kip-inch. So now that we have the torque, we can plug that into this equation now. So our shear allowable, we said, is 10.5. Our torque is given as 16.4, or we found that. Rho, that's going to be your, in this case, outer diameter or outer radius. You could put any point you want to find the stress at, but in torsion, our max stress will be at the farthest out point. So for a diameter of 4 inches, our outer radius will be 2 inches. and divide that by j. We're hollow, so it's going to be pi over 2 times radius outer to the fourth minus radius inner to the fourth. And you could have put in radius outer minus thickness. That would have worked too. So solve that, and we end up getting the inner radius to be 1.935 inches. We know the thickness is radius outer minus radius inner. So we get 2 minus 1.935. We get a thickness of 0.065 inches. It wanted us to round up to the nearest 16th inch. So I'm going to multiply that times 16 over 16. So 0.065 times 16 gives us 1.04 over 16. So always round up, make it bigger than it needs to be. We'll get a thickness of 2/16, which is really just 0.125 inches. So now we're going to do the same thing, except for the drive shaft, or the solid axles here. And this will be a little bit easier because it's solid. There's just an outer radius. The inside is completely filled. So we're still at 840 horsepower. That is true throughout the whole system. Our axles are spinning at 867 RPM. Okay, so come down here. It's the exact same steps. So power, we already said, is 462,000, and that's in the pound-feet per second. Equals torque. Our angular velocity, we said, was 867 revolutions per minute. And again, same steps here. In 1 minute, there's 60 seconds. And in 1 revolution, there's 2 pi radians. And again, we're going to convert that from pound-feet to kip-inch. So we end up getting a torque of 61.1 kip-inch. So now that we have that, we can plug that in our shear equals T rho over J. Again, we're using that because that is the only stress that develops due to torsion. We said our allowable shear is 10.5 KSI. We found our torque to be 61.1. Rho will just be outer radius, which we don't know yet. And on bottom we get pi over 2 times the radius, or radius outer, same thing, to the fourth. We end up getting a radius of 1.547 inches. It wants us to round up to the nearest 10th inch. So that one's a little bit easier. We can just 1.5 goes up to 1.6 inches.